Databases are essential components of modern software applications. They provide a structured way to store, manage, and retrieve information efficiently. From online shopping carts to social media platforms, databases power countless applications we use daily. Understanding the basics of databases is crucial for anyone involved in software development or data management. A database is essentially an organized collection of data. This data can be anything from customer details and product catalogs to financial transactions and scientific observations. Databases are designed for efficient storage and retrieval, allowing users to access and manage vast amounts of information easily. Imagine a library with millions of books. Without a proper cataloging system, finding a specific book would be nearly impossible. Databases serve a similar purpose in the digital world, providing a structured system for organizing and accessing information. In today's data-driven world, businesses and organizations rely heavily on databases to make informed decisions, improve operational efficiency, and gain a competitive edge. Whether it's analyzing customer behavior, tracking inventory levels, or managing complex financial transactions, databases play a pivotal role in modern business operations. Database design is the process of creating a blueprint for a database. It involves defining the structure, relationships, and constraints of the data to ensure its integrity, efficiency, and scalability. A well-designed database is crucial for the overall performance and reliability of any software application. Effective database design ensures that data is stored in a logical and organized manner, making it easy to access and manage. It also helps to eliminate data redundancy, which can lead to inconsistencies and errors. A well-designed database also improves data integrity by enforcing constraints and rules that prevent invalid or inaccurate data from being entered. Moreover, a well-designed database can significantly enhance the performance of an application. By optimizing data structures and relationships, database designers can minimize the time it takes to retrieve and process information. This is particularly important for applications that handle large volumes of data or require real-time data processing. In essence, database design lays the foundation for a robust and efficient data management system. A well-designed database not only ensures data integrity and efficiency, but also enables organizations to leverage the full potential of their data assets. The first step in database design is to gather requirements. This involves understanding the needs of the application and the users who will be interacting with the database. It is crucial to identify the entities, attributes, and relationships that need to be modeled in the database. For instance, if we are designing a database for a library, we need to identify entities such as books, members, and loans. We also need to define their attributes such as book title, author, member name, and loan date. Finally, we need to establish the relationships between these entities, such as which member has borrowed which book. Requirements gathering often involves collaborating with stakeholders, conducting interviews, and analyzing existing data sources. The goal is to gain a comprehensive understanding of the data that needs to be stored, the relationships between different data points, and the expected usage patterns of the database. Gathering detailed and accurate requirements is essential for the success of any database design project. It helps to ensure that the database meets the specific needs of the application and the users, avoiding costly rework and data inconsistencies down the line. Once the requirements are gathered, the next step is to create a conceptual database design. This is a high-level representation of the database structure independent of any specific database management system, DBMS. Entity relationship diagrams, ERDs, are commonly used to visually represent the entities, their attributes, and relationships. ERDs use symbols to represent different components of the database. Entities are represented by rectangles, attributes by ovals, and relationships by diamonds. For example, in a library database, the book entity might have attributes like title, author, and ISBN, while the member entity could have attributes such as name, address, and membership ID. The relationship between these entities, borrows, would be represented by a diamond connecting the two. The conceptual design focuses on the what of the database rather than the how. It outlines the key entities, their characteristics, and how they relate to each other without delving into the specifics of data types, storage, or implementation details. This abstract view of the database allows designers to focus on the overall structure and relationships, ensuring clarity and consistency before moving on to more technical aspects of the design process. Section 5. The logical framework, mapping concepts to structure. The logical database design phase translates the conceptual model into a structure that can be implemented using a specific DBMS. This involves, mapping entities to tables, attributes to columns, and relationships to keys. For example, the book entity in our library database would become a table named Books, with columns for title, author, and ISBN. Similarly, the member entity would become the members table, with corresponding columns for their attributes. The relationship borrows would be implemented using foreign keys in both tables, linking each loan record to the respective book and member. Different database models, such as relational, hierarchical, or object-oriented, can be chosen based on the project's specific requirements. Each model offers unique ways to organize and manage data, and the choice often depends on factors like data complexity, scalability needs, and the chosen DBMs. The logical design stage bridges the gap between the abstract conceptual model and the concrete physical implementation. It provides a structured blueprint that guides the actual creation of the database within a specific database management system. Section 6. The physical manifestation database implementation. The final stage of database design is physical design. This involves defining the physical storage structure of the database, including data types, indexes, constraints, and file organization. The goal is to optimize the database for performance, scalability, and data integrity. For instance, choosing the appropriate data type for each column is crucial. For a book's title, a string data type would be suitable, while the publication year would require a numeric data type. Additionally, creating indexes on frequently queried columns can significantly speed up data retrieval. The physical design phase also considers factors like data security, backup and recovery strategies, and performance tuning. It often involves close collaboration with database administrators to ensure the database is implemented and configured optimally for its intended environment. Physical design transforms the logical blueprint into a tangible database ready to store and manage data. This stage requires careful consideration of technical details and optimization techniques to ensure the database performs efficiently and securely in a real-world setting. Section 7. Popular database models, ERD, relational, and more. Several database models provide frameworks for organizing data. Each model has its strengths and weaknesses, making it suitable for different types of applications. Entity Relationship Model, or ERM. This model, often represented visually using entity relationship diagrams, or ERDs, is widely used for conceptual database design. It represents data as entities, objects, or concepts, and defines relationships between them. This model helps visually understand data relationships, making it easier to design and communicate database structures. Relational model. This is the most common database model where data is stored in tables with rows and columns. Tables can be related to each other through foreign keys, enforcing data integrity and enabling efficient querying. Relational databases are highly flexible and scalable, making them suitable for a wide range of applications. Object-oriented model. This model combines data and behavior into objects, encapsulating both data attributes and actions that can be performed on that data. This model is suitable for applications dealing with complex data structures, such as multimedia databases or geographic information systems. The choice of database model depends on factors like the complexity of the data, the relationships between different data points, the expected usage patterns, and the chosen DBMs. Section 8. Best practices for robust database design. Following best practices during database design is crucial for creating a robust and efficient database. Normalization. This process involves organizing data to reduce redundancy and improve data integrity. It involves breaking down large tables into smaller, related tables and defining relationships between them. Normalization helps eliminate data anomalies and ensures data consistency. Naming conventions. Using consistent and meaningful names for tables, columns, and other database objects is essential for maintainability and readability. Clear and descriptive names make the database easier to understand for both technical and non-technical users. Data integrity and validation. Implementing data constraints and validation rules ensures the accuracy and reliability of the data stored in the database. Constraints like data types, unique keys, and foreign keys enforce data integrity at the database level. Indexing. Creating indexes on frequently queried columns can significantly improve query performance. Indexes act like lookups, allowing the database to retrieve data faster without scanning the entire table. Documentation. Thoroughly documenting the database design, including ERDs, data dictionaries, and design decisions, is essential for future reference and maintenance. Adhering to these best practices results in a well-structured, efficient, and maintainable database. Section 9. Tools of the trade, enhancing design and modeling. Numerous tools are available to aid in database design and modeling, simplifying the process and improving efficiency. Database design tools. These tools provide visual interfaces for creating ERDs, designing database schemas, and generating SQL scripts for database creation. Examples include MySQL, Workbench, Microsoft SQL, Server Management Studio, and Oracle SQL Developer. Data modeling tools. These tools focus on creating conceptual and logical data models, often with advanced features for data analysis, collaboration, and documentation. Examples include Irwin Data Modeler, IBM InfoSphere Data Architect, and SAP Power Designer. Collaboration and version control. Using version control systems like Git allows multiple designers to work on the same database design project simultaneously, tracking changes and facilitating collaboration. These tools not only streamline the design process but also help enforce best practices, improve documentation, and enhance the overall quality of the database design.